Hey everybody, it's Mr. Ray here with our first lesson in grade 11 University Math unit on functions and transformations. So this lesson is entitled Functions, Domains, and Range. Sorry, Functions, Domain, and Range. So we're going to basically, the main part of today's lesson will be what's the difference, what is a function and how does it compare to what we call a relation. How do we know the difference? How do we know if something's a function? And then basically, how do we define the domain and range of a function or a relation? So we always start off with a relation. So a relation is just a pattern between two variables. So this could be just, could be any random set of ordered pairs, like a table of values. You can also define a relation by its graph or an equation, and we're going to be looking at all of these ways. But a relation, there's really no constraint on what those values can be. What could the graph look like? What could the table of values look like? There's no constraint. You could just pick any sets of values you want. Okay. Now the next thing, which is, this is the name of the course, function. Okay, so a function is a relation. Okay, so it is all of these things we've just talked about. It can, it's a set of ordered pairs. It's a graph. It's an equation that defines a relationship between two values. But there's one major constraint for a function, and that is that the independent variable, which normally we call x, the first variable, first coordinate, corresponds to exactly one value of the dependent variable. Okay, so that, if I was to paraphrase that, that means for each value of x for the function, there's only one value of y. Okay, so for example, I couldn't have 0.25 and a 0.23 because that has the same x value, the independent value of 2, but it has two different values of y. Okay, that would be totally fine to call a relation, but it does not pass the test which defines a function. Okay, so if you were to look at it, how these relation and functions are related, you could say that all functions are relations, but not all relations are functions. So if I was to do like a little chart for that, I could have a big circle that defines all the relations, and then inside there is another circle that defines all the functions. Okay, so that kind of tells you that all functions are relations, but not all relations are functions, because there's some relations that fail this test that we just talked about. Okay, so we're going to be looking at different ways of representing relations and functions, and how do you know if it does pass the test of being a function. Okay, so the first test we have is when we have a graph. Okay, we have something called the vertical line test, and we're going to practice this basically to determine whether that relation is a function or not. Okay, we'll get to that in a few minutes. And then we have domain and range. These are important definitions for today because we're going to be defining domain and range for a relation or function. And quite simply, the domain is the set of all the possible x values of a relation or a function. And the range is the set of all possible y values, the second coordinates. Okay, they don't say x and y here, just because you could have a relation that doesn't use x and y. It could be, I don't know, a and b, or any sets of variables you want. So the range refers to the dependent variable, and the domain refers to the independent variable. Okay, also we're going to need to know what this real number thing is, and I'll get to that, but basically we have a special symbol. It looks like kind of a strange looking capital R. I'll tell you how to draw that when we get there. But basically a real number For the purpose of this course, a real number is any possible number. Okay, now in the mathematical world, that's not entirely true, but for us, it could be any integer, decimal, a decimal that stops or a decimal that goes on forever, a fraction, any of the numbers we're used to working with, we consider to be real numbers. Okay, and we'll talk about asymptote. This is going to be something that's you're going to see in grade 11 and 12. We'll talk about that when we get there. Okay. Now the key concepts, I've already talked a little bit about this. A relation is a function if for each value in the domain x, there's exactly one value in the range y. Okay. We use the vertical line test on a graph to determine if it's a function or if it's just a relation. Okay, we'll talk about that. And we'll talk about domain and range when we do the examples and this set notation as well. We'll do that at this point. Okay, so example 1, we've got different graphs of, well, for the time being, we can definitely call them relations. Whether or not we can call them functions, that's what we're going to determine. So it says, use the vertical line test to determine whether each relation is a function. Justify your answer. So what the vertical line test is obviously a vertical line is a line, for lack of a better prop. My pencil is a vertical line. So I would, if I scan through the graph with this vertical line, what the vertical line test does is if at any point that vertical line touches more than one point on your graph, then you've failed the test. And we'll talk about why it fails in a second, but this test you use for any graph. So if I'm looking at this line in example A here, if I pass my pencil, now the pencil's pretty thick, so just consider the edge of the pencil. So at any point as I scan across here, the right side of my pencil is only touching one point on the line. Okay, so that means it passes the vertical line test. Okay, so because it passes the vertical line test, there was no point when I went across here that the right side of my pencil touched more than one point on the line. It passes the vertical line test, and therefore it is a function. And the reason is it passes. Now, I'm not going to write vertical line test every time I do this, so I have a short form VLT. Okay, so we know without doing the vertical line test, we know these are all relations because it's showing some kind of pattern of how the points x and y values relate to each other. But we use the vertical line test to say it, to answer the question, is this relation a function? Okay, so if we go to B, this time as I move my vertical line test, or my vertical line, the right side of my pencil, as I touch the edge of this, the very first time I touch it, it's only touching one point. But as soon as I move it a little bit more to the right, you can see for the rest of this motion, the pencil is always touching 2 points on that graph. So because, and it doesn't have to be a certain number, it's just once. All it takes is one time to touch 2 points, and it's going to fail the vertical line test. So the criteria for passing is at no point will you ever touch 2 points with your vertical line. So in this case, this is not a function, but it is a relation still. And the reason is it fails the vertical line test. And you can see it fails it many, many times. Okay, now if we go to the third graph, this is straight from grade 10. We've got a parabola here. As we move our vertical line across the graph, okay, you can see it's only touching once. Okay, even at the top, it's once, and as I continue, it's only once. So for this graph, for this parabola, for this quadratic relation, this is a function because it passes the vertical line test. Okay, and then we move to this graph. Obviously that's a circle, and hopefully at this point now you can tell without even putting a pencil or a vertical line. You can tell as I touch the left side of the circle that one moment it's only touching the circle once, so it's passed so far. But as soon as I go to the right, it's touching the circle twice until I get to the edge on the right, touching once and then not touching. So this has definitely failed the vertical line test, so it's not a function. So a circle is not a function, but you can tell, you know, this line and maybe most lines and quadratic relations are functions as well. Okay, so that should become pretty quick for you to be able to do. If I give you any graph of some kind of relation of points or curves or lines, you should be able to quickly tell me, yes, that's a function, or no, it's not, just by moving your vertical line across. All right, now we get into domain and range. So it's saying for each, using the graphs of these functions or relations, write the domain and range. Okay, so this will be brand new for pretty much everybody that's just starting grade 11. Now for the domain, I'm going to list them both. Now the notation here is important, okay? Don't take any shortcuts in the way you do this. So to write what the domain is, we always start off with a capital D and then a colon. This is basically saying this is what the domain is to the right of the colon. And then we have squirrely bracket or parentheses. Okay, I don't want you to do just a round bracket, so no shortcuts here. And then we talk about, since the domain is we're talking about the independent variable, so to be totally accurate, we would need to go back to our graph and say, well, what is the variable for this graph in A? What are the variables we're using? What's the independent? What's the dependent? So in this case, you can see the X there. That tells you that's the independent variable because it's the horizontal axis. And the vertical axis has the variable Y. That's going to be your dependent. So your domain will refer to the possible values of X, and the range will refer to the possible values of Y. Okay, and if we quickly scan at the other graphs, you can see they're all using X and Y. Okay, so these will all use the same variables, but it's something you should be careful of because I could just as easily give you a graph that uses the variables T and H. So in that case, you're not going to be putting X and Y here. You're going to be putting putting T and H. Okay, so just be careful of that. Now, if I go back to this first graph and I ask myself, what values of X can this line have? Okay, now you have to use your imagination a bit because we've got arrows at both edges of the line. So the line doesn't end here and end here, it continues on forever. Now because it continues on forever, if you think of the possible X values, is there ever an X value that this line won't reach? Well, if I continue this way, I'm going to pass through all the positive X values. Okay, it may not look like it because it's pretty steep, but if you run this line infinitely, it can reach every X positive value. And if I go upwards on the graph here, it's eventually going to reach all the negative X values that you could think of. Okay, it might take a lot of time, but it will reach it. So because for this graph, this line, we start off by saying, well, what are the values that X can have? So we put the variable, and then we have this Greek symbol, epsilon. Okay, it's kind of like a C with a line in the middle. It's like a letter E, but more curved. That basically stands in math that says X is an element of, basically, where can we get the values of X? And this is where we introduce that funky looking R symbol that we had here. well, it was up here, I think, as well. So real numbers, we use the symbol, it's like an R with an extra line. That stands for all possible numbers for this course, at least. So because x can be any real number, any number at all, we put that symbol, okay? So that basically says there's no restriction on x. X can be anything you want, okay? And now we go to, so we've defined the domain, now we define the range, and we start with an R. Now this is not the same R as the real numbers, sorry. That's not the same R as the real numbers, it's just a regular capital R. Okay, and again we do the colon, parentheses, and now we use the variable for the range, which we've already said is y. Now, in terms of the y values, this is a little more obvious because you can see that, you know, this direction, it's going to cross all potential, all possible positive y values, and going in this direction, it's going to cross through every possible negative y values. So again, we have the same notation for this. X can be any number or any real number. And then we have a closing parentheses there. Sorry about that. So this basically is telling you that for that graph, you can have, it will eventually, it can touch any x value, it can touch any y value. There's no restrictions. And that's what no restrictions looks like. Okay. For the graph B, so let's start off with the domain. The domain are the possible x values. Now this looks more restrictive because I can see right away this graph will never come over to these values of x here. And you can see that, you know, there's a value for x equals 2, and anything higher than 2, because it actually goes in that direction twice, but anything below 2 won't be part of the domain, won't be a valid x number. So now when I define the domain for that, okay, now because it can be any number, any fraction, decimal, integer, I always start off with the same thing I had above, but I put a restriction. X can be any real number, but x has to be greater than or equal to 2. Okay, it can definitely be equal to 2 because of that point right there, and anything bigger than 2, obviously, from the curve there. But that's a restriction that says x has to be greater than or equal to 2, and if it is, it can be any real number. It can be a decimal, fraction, integer, anything equal to or above 2. So that's how we define the restriction. We first say that it can be anything, and then we qualify that by setting a restriction. Okay, it's not enough to just say that x is greater than or equal to 2 for reasons that we're not going to talk about in this course too much. We will eventually, but for now, just take it as scripture, math scripture. Okay, and not the range. Okay, you ask yourself, usually I ask myself, are there any values of y that this graph will never reach? And if I look at this branch of the graph, I can see this is going up forever. So it'll eventually reach any positive y value. And the same thing for this branch, it's going down. So it'll eventually reach every negative y value. So basically that tells me there's no restriction on y. Y can be any number. So we always start by saying y is an element of R, real numbers. Now, if there was a restriction, I would put it here, just like I did here. But in this case, there is no restriction, so we just leave it as y is any real number. Okay, now let's go to the third graph. The third graph is a parabola that's opening down. In terms of the x values, hopefully you remember this from grade 10, these arms of the parabola are continually going outwards. So in terms of x values, these branches will reach any x values along here. So for any, and this is true of any parabola, there's no restriction on the domain. So we say the domain x can be any real number with no qualifier. Okay, and then for the range, well, the range is a little different because you can see, well, the bottom part continues forever. So I can reach any negative y value I could think of, but in terms of going upwards here, this vertex here kind of defines the highest point, the highest value of y that I can reach. And for this parabola, it's 3. Okay, so I can have my y values anything less than or equal to 3. So, but we always start off by saying y can be any real number to define the types of numbers it can be. It can be fractions, decimals, and integers, but we put the comma there to qualify. Y has to be less than or equal to 3. Okay, and then the last graph, the circle. Well, you can see the circle, it's got restrictions on both because there, if I look at the x values, well, the smallest x value I can get would be, looks like -3, because the circle will never go beyond less than -3. It'll never go higher than 3 for x, and I've got a similar restriction for y. Y will never be higher than this value, which is 3, and oh, sorry, that was 5 there, not 3, and it will never be lower than, well, not that point there, this point right here, which is 5, sorry, -5. Okay, so this domain and range is a little more complicated. So remember the x values. Start off by saying it can be any real number. However, this has a lower bound and an upper bound for x. X has to be between -3 and +5. So I know students sometimes have difficulty with this. We call this set notation. So we start off with the x in the middle because we have a higher and a lower bound. The highest it can get would be 5. Go back to here. Highest it can get is 5. The lowest it can get is -3. So I put the higher bound on the right, lower bound on the left, and then this is higher, so the inequality opens towards the higher one. So I've got that. Now you ask yourself, okay, I've kind of got the upper and lower bound, but can it actually have these values? And it can. The circle does touch both of these, so that's when you put your equal sign there as part of the inequality. Okay, so that's obviously more complicated, but that's going to help us with the range for this circle. Okay, so we start off the same. Y can be any real number, and y also has a restriction at the top and the bottom. So the highest it gets is 3, the lowest is -5. So again, I'll set that up the same way. The lowest it can be is -5, highest it can be is 3. The inequality sign, it should always point to the left on both sides. If you put the higher number here, the lower number here, and then this is also equal sign because the y values can be 3 or -5. Okay, so that's how you define the domain and range. So this way of writing this is brand new. And again, I don't want you to take shortcuts. I want you to write it exactly the way I've shown it here. Okay. Now, so we've looked at some graphs. We did the vertical line test for the graph. However, not all relations and or functions are given by a graph. There's other forms. You could have a table of values. You can have a set of order points. You can have an equation. We'll look at the equations later, but example 3a, we've got a set of ordered pairs, and this is really similar to a table of values. It's just listed as the x, y pairs of numbers instead of B is actually a table. So you know, I could create a table of values from this, and I could create a set of ordered pairs from this. It's just the way it's written. Okay, the first value in the ordered pair would be your first column, your x value normally, and the second number in the ordered pair is your second column, and we could refer to that as the y, or we could say this is the independent variable dependent, just as the first coordinate is independent, the second is dependent. Okay, so determine the domain and range of each relation, and then use the domain and range to determine if the relation is a function. Okay, so this is a little bit different. This relation is just defined by these 5 points. It's not a line that goes through these points or a curve. It's just these 5 points. So now you can kind of tell, if I look at the order here, it seems to be kind of random. So I'm going to do the domain first. So the domain here, capital D, and I'll use variable x just by default. Now I can't say this is any real number. These are only integers. The only values of x we can have are -3, 5, -2, 5, and 6. Okay, so I don't start an ordered pair off. I don't define the domains. Sorry, I don't define the domain by saying x can be any real number, because it can't be. It can't be decimals. It can't be fractions. So what we do for this is we just list them. Okay, so instead of saying what it can't be is an infinite list of numbers. So we just define, in this case, for the ordered pairs, we just define what the possible values of x are. So I'm going to put them in numerical order, ascending order. So I've got -3 is my most negative, -2, 5. I've actually got 2 values of 5 there. I only put it here once. Okay, and then 6. And then I just end it with a parentheses. So this, unlike the previous domain and range, where I kind of said we're going to start off with all the real numbers, and then I'll restrict it. This is restricted, obviously, but instead of defining what it can't be, I'm defining what it can be. There's only 4 possible values of x, so we define it right there. Same thing for the range. So I'm going to use the variable y, even though it's not listed there. I'll just take a chance that that's the variable. Now these are also not in any kind of order, so if I put them in ascending order, I got -8, -6, 3, 4, 7. Okay, now it says use the domain and range to determine if the relation is a function. So I'm actually going to do 2 ways. You can use the domain and range. If you look at how many possible values of x I can have, there's 4 values here for x, but there's 5 values for y. So that tells you, if this is true, that must mean that one of these x values has more than one y value. Okay, just logic. So you could make an argument for that, and that would be awesome. And that's kind of what they're asking you to do. But I think in most cases you wouldn't just use this count here. What I'm going to do is look for any violations of what it takes to be a function, and that means, so remember, the definition of being a function is there's only one unique y value for each x value. So if I see an x value repeated, and I do, I see that 5 is repeated. Now I might for some reason they might have listed the same point twice, and that would be okay. That would not violate the definition of a function. But if these 2 y values are different, which they are, that tells you that this cannot be a function. Okay, so the argument, usually the way we would answer this question is we have multiple y values for x equals 5. And that is a clear violation, so therefore it's not a function. And I'd like to kind of relate this back to the vertical line test. If you, I'm just going to do a very crude sketch here. If I was to plot these 2 points here, I'd have 5, 3, so say that's 5. I'd have a point here, and -6 is down here. So that's 5, 3, and that's 5, 6. Okay? If I graphed those, if I plotted those points, you could see if I did the vertical line test, it fails because those 2 points are directly above each other or below. Okay? And if you have 2 points directly above, that means the vertical line test will touch them both, and therefore it will fail the vertical line test. So that's how you could kind of relate this rule back to the vertical line test if you graphed it. Okay, let's try this last example. This time the relation is given in a table of values. Shows the number of children of each age at a sports camp. Okay, so if you were consider this a relation, you don't even have to check the numbers. It's just a set of entries in a table of values, or an ordered, you could turn this into ordered pairs. This is definitely a relation, but how do we know whether it's not a function? Well, let's first of all do what they asked us to do. Let's do the domain and range. So again, we're going to do it exactly like we did these, but this time we just look down the columns. So x is the age value, the independent variable. X can be 4, 5, 6, 7, 8, 9, 10. So I'm actually going to list all of those. And it's important to list them because if I said x is between 4 and 10, that might imply that, well, could it be 4.5? No, it can't. So if I just list them here, it makes it very, very clear that these are the only possible values. And then for the range, we do the same thing. These are out of order. I'll put them in ascending order just so we can compare them. We've got 5, 8, 9, 11, 12, 14, 22. Okay, and you notice I didn't, I didn't repeat anything that might be duplicated in either of these domain and range. And I've got, I should have exactly the same number. So I've got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 6, 7. So I've got 7 values for x, 7 values for y. So that in itself should be enough to say, well, that has to be a function because you can't have more than one x, you can't have more than one y value for a specific x value. But you could just go back to the table here. Now, as long as I don't have more than one entry with the same age, everything's cool. So the fact that all of these are unique, that tells me that it is a function. So I could make the argument each age has a unique number of children. So therefore it's a function. Okay, so that wraps up our lesson. Got some homework questions here to try out, to practice. But if you kind of recap what we've learned that how relations and functions are related, that all functions are relations, but not all relations are functions. Functions have a restriction that you have to have a unique, basically y value for every x value. And then we looked at ways of determining based on the data that was given to us for the relation. So if you have a graph, it's very simple. You just do your vertical line test, see if your vertical line ever crosses the graph at more than one place. If it does, it fails, and it's only a relation. If it passes, it's a function. And then we looked at these ordered pairs. We looked at a table of values. We can tell if looking at them, is that data reflect a function, or is it just a relation? Okay. And we also learned about domain and range, how we write them in terms of the notation, and how we actually gather the information, in this case from the graph, but we also did domain and range from a table of values and a set of ordered pairs. So those are the two important things: domain and range, and does this data reflect a function, or is it just a relation? Okay, so that's it for today. We'll continue on with the next lesson. So have a great day.